Hello, Alex. Thank you for your time today. Please tell us a little about yourself before you begin with your topic.
Yes, hello everybody. Thank you for the time and thank you for still joining. Now I have the last part for today, the last 30 minutes. Maybe it's 40 minutes, let's see. And my topic is the DC-DC converters and the secrets of power inductors. So now we are moving a little bit away from the capacitors because today we have seen or heard a lot of capacitors. And now we are going more into the inductor world. Some words about myself. I'm a field application engineer located in Germany. I have experienced 2 years as a research and development engineer. Then I moved to a sales company, and now I'm already since 10 years FAE for passive components, and I'm supporting German automotive customers. The content of the topic today, I want to show a little bit more deep in the DC-DC converter. I have a nice, interesting calculation example. And then I want to talk about the passive components, mainly about the inductors. And then I give you some Camet solutions, followed by an outlook, what is coming next and what is planned. So let us first start with a short view on a DC converter. Here I took the example of a buck converter. And I guess you have all seen this before. So this might not be something new for you. You have an input voltage, you have a switch, and then a diode. And either the switch is on or the switch is off. You have, with a switching frequency, a nice on current and off current. Very simple technique. And then you have the inductor current. And this is finally the ripple current. And what we see here, this is something we try to have as minimum as possible. So, and here we are now. So we have the ripple current, and this is mainly given by the inductance value, but also by the current and the duration. And this is the challenge because the lower the ripple is, the better it is. But we cannot reduce the ripple to 0. So, and now when we look at the switching frequency of my DC-DC converter, the most common switching frequency are somewhere around 300 kilohertz to 3 megahertz. And with increasing switching frequency, the recommended inductor size is reduced. This is ideal for reducing space on the board. The current from a switching regulator has AC components, and that will flow through the output capacitor. And therefore, the output capacitor ESR defines the ripple voltage generated by the AC component of the current. So now, what defines finally the inductance we need? First, we have input voltage, or the maximum input voltage. Then we have the output voltage, and for sure the switching frequency, the output current, and the maximum allowed ripple current. Well, let's go 2 pictures back where I showed you a buck converter, or we can also take a boost converter. And as there's always something in common, it's always you have an inductor and a capacitor. And these components you can get from Camet. And the inductor is much more complicated to design ideally. And if you look into the inductor worlds, also from competitor, you may find thousands of different types. And the easiest way is try to use the one which is recommended in the IC datasheet. So here this might be a good start. But also I have seen in some IC recommendations that the inductor which is given is not the best solution. It might be a good solution, or but not the cheapest solution. So in this case, if you want to have a cheap solution and also to have a small solution, you might have to look twice. And here I want to help you to find the best solution. So let's look into the inductor. The inductor formula is given here. And the 3 important characteristics for the choice of the right inductor is the frequency, the maximum current, and the inductance value. Well, the frequency is not given in this formula. You can find maybe the frequency which is in the mu r, because the frequency is something which depends on the material. And the maximum current we do not find here, but the maximum current is also given in the length of the wire and also in this wire structure. Even if you're using a round wire or flat wire. Now let's look a little bit more deeper into this formula. If you look at this formula, we can see the more turns we do, the higher we get the inductance, or in this example, it's the impedance. But what happens also is that we move the resonant point to a lower frequency range. And this means, for sure, you can increase your number of inductance, your number of turns, but this will also change your frequency behavior. So it's not so easy to just put hundreds of turns on an inductor just to have a higher inductance value. At the same time, you will change your frequency band, and this will lower the resonance point. Also, when you take different material, for example, the most common used material you find in the market is manganese zinc or nickel zinc. You can get different materials, and also from Camet, the S18H describes that you have something around 18,000 for the magnetic permeability. And if you have 10H or 5H, this is 10,000 or 5,000 for the magnetic permeability. If you are using now nickel zinc material, which has a higher frequency range, this means that the maximum magnetic permeability is much lower than what is possible with manganese zinc. And this could be a problem, because here you cannot get the same impedance or inductance value. So also here you can see, by using a different material, you have a different behavior, not only in the frequency range, but also in the maximum magnetic permeability. And the maximum magnetic permeability describes the inductance. So also here you have to look twice. Well, let's make it very simple. If you want to use a manganese zinc material, you have a lower frequency range, and nickel zinc, you have a higher frequency range. What does that mean? Now here I can see manganese zinc is something around 1 megahertz. That seems to be nice for my DC-DC converter. And the nickel zinc is somewhere much higher. But it isn't, unfortunately, that easy, because with this picture, you would always choose manganese zinc, right? Unfortunately, it's not so easy. And I will make it a little bit more complicated now. Let's say I don't make it complicated, I make it complex. Because the permeability is complex. And you have two parts. The one is the mu prime and the other is the mu double prime. The one is the inductive part and the one is the resistive part. At first, you have an inductive part where you have an ideal inductor. And mu double prime is the resistive part where you have losses. And the higher the frequency get, the more losses you create. So your application defines which value is more important. For us, we are today looking at the DC-DC converter, not at a filter, not at a ferrite choke or whatever. So we don't want to have high losses, we want to have low losses. And low losses means I need a high mu prime, which is the gray curve, and a low mu double prime, which is the blue curve. And this means we have to avoid that we get into a higher frequency. And by remembering, I will now go one slide back. By remembering that we have here the manganese core, at this point, the losses might be already too high. So for something in the megahertz range, it might be better to use nickel zinc material. So always keep that in mind when you choose a component by its material. Now, the second one is the inductance value. And for sure, the inductance value is the most important thing by choosing an inductor. And normally in your IC papers, you see which inductor is recommended. We know that the inductance increases with a higher permeability, but also with a bigger cross-section of the core, with a higher number of the turns. So, but we want to keep the component performance by having a bigger, having a higher permeability. So we need lower cross-section of the core, which gives us less weight and a smaller case size. Also, we want to have less turns, because then we can use thinner wire, and this gives us more RDC resistance. And you see, it is getting more and more complicated. Now, this formula you can get anywhere in any calculation for a buck converter. I've chosen a buck converter. For a boost converter, it's a similar calculation. Maybe you have seen this before. I take an example. Let's say we have 36 volts input voltage, and I want to have 5 volt output voltage with 1 amp. I define that the ripple voltage and the ripple current is 300 milliamps, and therefore, and also the frequency I took 350 kilohertz. These are just example values. It's not a given value, it's just one example. Now, what happens if I calculate now? I get 40 microhenry. And now the question, which value do you want to take? 33 microhenry, 47 microhenry, or 39 microhenry? What is the best solution? Well, let's assume we don't want to take 57 microhenry because we assume that the maximum current is lower, our DC is too big, or the item is too big. We don't want to use the 39 microhenry because it's a special item and it's not available from all manufacturers. And we always want to have a second source. So let's start to calculate with the 33 microhenry. It's just 7 microhenry below this one. Should be a nice solution. Now I start the calculation. Let's assume we have in addition 10% inductance loss due to the saturation or maybe due to the manufacturing tolerance of the item. So in this case, our remaining inductance of the 33 microhenry is only 30 microhenry. So 30 microhenry is already 25% less than initially calculated because we calculated 40 microhenry. And if I now put this into my calculation, the voltage, the current, and the frequency are constant. So if we lower the inductance by 25%, we get a higher ripple current because this is the only thing which can be changed. And the ripple current is 33% higher, which is a lot. So in this case, we should not start by using the 33 microhenry inductor. We should start maybe by using the 47 microhenry inductor. So please use the higher inductance value to start your testing and not the lower inductance value. So for those of you who are wondering how I calculated a 33% higher ripple current when you have a 25% lower inductance, yeah, there's a simple calculation and I don't want to make it too long. 25% lower means the remaining inductance is 75%. These are 3 quarters. And this means we have 4/3 I ripple current, which is 1.33 I ripple. So just a simple calculation. We can calculate this later, but just keep in mind, if you have a lower inductance, you have a much higher ripple current, and you do not want to have a higher ripple current because this might affect your EMC. Now, let's make it much more interesting and have a look in the data sheet, because this is very important to find the right component. You can always take for your current 20 amp item, but this is too expensive, this is too big, it's too heavy. It's always the best to choose the slowest possible item you can find. And now looking in the data sheet, and this is a Camet data sheet, what can I see? 3 different current values. But now, which one is the current value I need? So the IRMS is the current when the temperature rise of the inductor is 40 K above the ambient temperature. Let's look into a picture. This means there's a current, and when you make or you increase the current more and more, there's one point when your inductor is 40 K higher or warmer than before with no current. And this is the point where we defined this is the IRMS. Well, we can also define the point where we have 60 K and then it's 3.9. Or maybe we defined, I don't know, 80 K, but this is just a definition. The saturation current is the drop of the inductance, what we have here, and we define it as -20%. So this is a totally different value and has nothing to do with the IRMS. The IRMS is something which has to do with the length of the wire and the cross-section, or the size of the cross-section. The inductance drop, the saturation, this is similar to an MLCC and the voltage of an MLCC. So here we have a drop of the capacitance, of the inductance. So the temperature rise and the saturation current are not standard values, and then they can vary from different manufacturers or even for one manufacturer. For example, these are some old components we sold some years ago. We still have them because we have no end of life. But you can see here, for this series, we defined already 20%. And here we defined an inductance drop of 30%. And you will find this in all competitors. So there's no standard rule and everybody does what he likes. If you ask me now, why are we doing this? The main answer is for some historical reason I cannot give you. So please keep in mind, the IRMS and the I saturation, they can be defined in different ways. There's no rule. And the same inductor is not the same inductor always. I give you an example, another example. When you look here now, if I define what I have given before, let's take the same inductor and define that the temperature rise is given at 50 K. In this case, you have a totally different inductor, but it's the same product. The same product looks different. It's actually the same. And we have the same with inductance drop. If I say my saturation current is defined by minus 30%, well, the current is much higher, but it's still the same item. So just a question. We define just one point on a curve and not a maximum value. Keep this please in mind when you are comparing different items. So the ambient temperature plus the temperature rise must be lower than the maximum operation temperature of the inductor. This sounds complicated, but I give you an example. Let's assume the ambient temperature of your application is 85 degrees. It's just an example. You decide to use an item with 155 degrees maximum operating temperature. This is given by the supplier, so by us. And our MPX series, for example, can be used up to 155 degrees. So this is a given fact, and this is coming from your application. I don't know this value, but I know this value. So, and now the maximum temperature rise of the inductor, very simple, is 155 minus the 85 degrees. The remaining temperature is 70 degrees. This means you don't have to have a look on the 40K self-heating. You have to look on the 70K self-heating, which means the maximum current of the inductor is higher than the IRMS value in the datasheet. But we cannot say how much the maximum current is because we don't know your application. This value, this 85 degree, this is something which is only known by you, by the designer, but not by us. So here we cannot give a maximum current. It's not possible for a supplier to give a maximum current because it always depends on your final application. And now I try to compare the same item. So I've chosen again one of our MPX series and a competitor. Well, what do I see now here? I started by having a look at the self-heating. And here I can see 3.3 amps, which is much lower. But in addition, the operating temperature range is plus 125 degrees. For our MPX series, it's 155 degrees. And this means, go one slide back, this means Camet has maximum 4.5 amps at 115 degrees. And this competitor item here has 3.3 amps at 85 degrees, considering the self-heating of 40 degrees. Here you can see the 40 degrees, but you have to take them away from the 125. So this means both items might look similar in some ways, but the Camet item can be used up to much higher temperature and up to much higher rated current. Also another example, it's also the same item. It's again 47 microhenry item. And here it might look, oh, the saturation current is 4.5 amps. But the saturation current of the Camet coil is only 4 amps. Well, let's take this one. It's much better. Unfortunately, we have to look twice again. Here we see the 4.5 amps looks better, but there's still the 2.2 amps. And we have here now the same situation. I cannot use this item at 4.5 amps. It's nice to know that there is a competitor who is selling a component which has a saturation at 4.5 amps. But by considering the rated current, that it has already a self-heating of 40 Kelvin at 2.2 amps, you will never get into the range of 4.5 amps. You never need to think about this. So this might look better, but it's not an issue for us. I don't care about this one because this is real important. The maximum current is somewhere given around, depending on your application, temperature at 5 amps, maybe 4 amps, maybe 4.7, I don't know. But with this item, you will never get higher than 3 amps, never, it's not possible. So here, the same looking item is worse. Finally, the maximum current, to give a conclusion for you. There are no standards in the inductor definition, so always look twice. The self-heating measurements are done differently, and this is also important. The size of the PCB, the duration of the measurement, and the cooling have an impact on the result. If I put the air conditioning on the component and then do my measurement, and then it looks much better in the datasheet. I don't know if someone is doing that. I'm not sure, but there's no standard rule. The current values, which are given in the data sheets, always reflect one point on the graph, but not the defined maximum of the inductor. And a similar looking item might sometimes not have the same values. But to make it very simple, if two same looking inductors from the size, from the material, from the soldering pad have different current values, most likely the difference between the items is not big. The definition, the data sheet might be different. So no supplier has big secrets which cannot be discovered. Believe me, whatever someone tells you, no one has a secret we don't know, and vice versa, to be honest. I'm just honest. I don't want to sell you something which is not true. Believe me, no one, when someone is coming to you and tells you he has the secret which nobody else had, don't trust him. And also consider your final application. This tells you what is really needed. And if you need support, we can help you to understand, to read our data sheet and to combine this with your application. Now let's go a little bit more into the product overview. And I have shown you already the MPX series, and this is our metal composite technology. We have also some older technologies, also with metal composite, always in standard series or ACQ200, and some older series which are not yet available as ACQ200. But with this MPX series, which I want to show on the next sheet, this is something where we cover nearly everything. And the most important thing is the last point, it fits to the common use soldering pads. So here you are no single source. It does not only look like the competitor items, it's nearly the same. And here we have a nice inductor range from 100 nanohenry to 100 microhenry. We can give you 100 amps, case sizes, standard case sizes from 5 by 5 millimeters up to 22 by 22 millimeters. And the operating temperature, this is something unique, 155 degrees. I would tell now we have found a secret at Camet, but 2 slides ago I told you something different. Never mind. But this is something which is an advantage for you by using the component at a much higher current. You can look here, and to understand this, you can find, let's take the light green curve, which is this one here. This is the 17 by 17 millimeter with a height of 7 millimeters. And if you want to have, let's say, a 10 microhenry inductor, you can find something up to 11 amps. This is how to read this sheet here. Let's have a short outlook on the Camet inductor series, what is coming next. So this is where we are standing now. We just have the MPX-V series for the automotive world. And the next step will be something which is also going much higher, the MPE-V series, and the E stands for extended temperature. So here we are going up to 180 degrees. Now, if you think, I don't care about your 180 degrees, I still take my 125, please consider the maximum temperature will give you a maximum current which is much higher than the standard item, because your self-heating can be much more than 40K. If your application voltage is something around 80 degrees, you can have a self-heating of 100 degrees. So this might be truly interesting. That doesn't mean that this is the maximum temperature of your application. This is the maximum temperature of the inductor. So self-heating plus ambient temperature. Just a short view into the inductor, because also the output inductor is not unimportant. And here I have an application example. We can see an MLCC, and this is an MLCC with DC bias. Just one example. If I want to have 22 microfarad at 5 volt, just one example, just one idea of myself. Then I can see I have already a capacitance loss at 5 volts. So, and here, this item is already 1210. In this area, I can easily move to a polymer tantalum solution. And this is available in the same case size. Either you can take this 3216 case size, 10 volt, 22 microfarad, or you can also move to a smaller item, which is an 0805. And this 0805 P case is just only 6.3 volt, which is still enough for your 5 volt application, but it's much smaller. And you won't get MLCC with 22 microfarad in 0805. Even at 5 volt, I guess it's not possible. So this item might be a nice drop-in replacement, especially when you do not want to have a DC bias. So the T597S case is a drop-in replacement for the 1206 MLCC, and the P case would be a replacement for the 0805. But for sure, nothing is perfect. There are some rules which needs to be considered. For the polymer capacitor, it's our 20 amps rule. So the maximum inrush current for polymer is 20, for polymer capacitor is 20 amps. And in the very first power on moments, all caps are short. This needs to be considered. And therefore, you usually need to take care of a soft start function. Usually, by taking at the output, this is no issue. Normally, by taking a polymer capacitor at the input side, this might be an issue. And the final slides, I just want to give you an overview of what series might be interesting in your DC-DC converter at the output. So I already showed the polymer capacitors, MLCC, no secret. But just have a look also on the aluminum-based capacitors, aluminum electrolytic polymer, or polymer can, or the conventional lytic. So this is a new technology. Everything which is in the green line, the polymer capacitor, is nearly the similar technique. And inside, we are not using a wet electrolyte, we are using a solid polymer aluminum. And this is a conductive solid polymer, which has various advantages, especially when you're looking at ESR, ripple current, but also when it comes to lifetime. And this is something which is always important when you think about aluminum electrolytic capacitors. Also, we do now offer a hybrid aluminum. So whichever technology you like, we can offer it. So coming to the next slide to show the different examples and advantages of the different technologies, what we can see now is for sure the polymer has an advantage. It has a low profile. You can replace with one polymer a bank of MLCCs, which is a cost-saving solution. You have a lower ESR, lower ESL. You have a replacement for MLCC, piezo noise. You have no derating. So the polymer capacitors are very good products. For sure, they are a little bit more expensive. But on the next slide, I want to show you that it's not always the most expensive solution. In this picture, I have marked as red what is maybe the downgrade and green what is perfect. So the ceramic capacitor is nice in the size, price, the size range, the frequency range is nice, and the price per piece. The tantalum polymer capacitor might be very expensive if I look just at one piece, and I agree. It's more than, sometimes it's more than 6-7 times more expensive. But I took an example, and the price per microfarad, in this example, I tried to reach 100 microfarad at 100 volt. The ceramic solution is not longer the cheapest, it's the most expensive solution. For sure, to reach 100 microfarad at 100 volt, you need several items in parallel, or some fancy size like 20-20 or I don't know what solution you may use. So in this case, here now the polymer tantalum solution is the cheapest solution. It's much cheaper also than the new aluminum polymer or the hybrid solution. if you're now looking at the price per volume, so I tried to put 10 microfarad in 100 cubic millimeters, then again, the ceramic capacitor is still the cheapest, and also the aluminum electrolyte, where we say which has the highest volumetric efficiency. And the tantalum polymer is mid-range. So from whatever side you are looking into the capacitor, you see that it has no solution which is always the best solution. And the best solution for you, and the same like in the inductor, is to always look into your application and then read the data sheet. You can see it might be the best solution to take a ceramic, but sometimes it might be the best solution to take a tantalum polymer because of the lifetime or the price per microfarad. Or maybe you might want to take an aluminum electrolytic because you need a high capacitance range. So it's always depending on your application. And for sure, you might find in the IC manufacturer data sheet some recommendation, but you can optimize your application, especially price-wise and size-wise, because this is something where the IC manufacturers do not look into. They are looking in their recommendation which items fits the best, but they are not looking which item is the cheapest or which item is the smallest solution. For sure, they are recommending not the smallest solution because then the DC-DC converter does not work perfectly. So you have to look twice. I hope in the last 30 minutes I could give this small tips. And with this, I'm now at the end of my presentation and I'm open to questions.
Thank you, Alex.